Hey guys, my name is Sikachev. I'm associate lead graphics programmer in People Can Fly, and I will tell you today about fluid-based wind simulation we did at People Can Fly and integrated it in Unreal Engine 5. So here's the talk outline. So we will first talk about related work in this field. Then next I will give my 101 version on the fluid sim. Then we will talk about how to use fluid simulation to actually simulate wind, because there are some challenges that are not that obvious. Then I will talk about Unreal integration, but frankly, the same advice could be applied for a lot of modern engines. And finally, I will show the results and present my thoughts on what could be the next steps of it, because this is very much work in progress. So let's start with related work. Here I put some of previous work both on fluid simulation and on wind simulation. So for the fluid simulation, the golden standard is kind of the GPU GEMS 1 and 3 implementation. So despite the code is a little bit antiquated and you might need to put some effort to make it run, there are already like multiple shader toy implementations. So it's a good starting point and you can get something running from there. Then there was a talk on the Shadow of the Tomb Raider fluid sim, where 2D fluid sim was used to do oil on water. And the biggest idea presented there was to have a scrolling simulation window following the camera, so you don't have to run the simulation in the entire world. And then the last thing that I wanted to mention for fluid sim related, it's Fluid Ninja. So this is a solution that is fully integrated into the Unreal Engine. And it's based on blueprints, so it's like it doesn't have any core alterations. So this is a big advantage of it. And it's just basically made for generic fluid sim cases like explosions, fire, you name it. And then I wanted to talk about two methods for wind simulation. So the most recent ones were God of War and Ghost of Tsushima. So in God of War, the biggest highlight was the way that they have separated local and global wind, and that they have different, for local winds, they have different motor types that they introduced. But one of the biggest limitations was that they never really handle obstacles, because the fluid simulation they do is based on simple diffusion. And then in Ghost of Tsushima, basically the approach was somewhat similar, but the presentation focused more on how different materials react on wind. So particularly, it's more, I would say, like tech art related, if you wish, talk. But there were some very interesting insights on clothing simulation, particularly how to not let different clothing layers intersect each other. So with all this related work, why am I talking here and what can we offer more? So first, as I've mentioned, the existing wind simulation didn't really handle obstacles in a consistent way. Yes, in Ghost of Tsushima approach, they made some basically some method to take landscape into account, but it was more like a special case. So therefore, we use fluid simulation, because in fluid simulation you can naturally have obstacles treated as boundary conditions. Then why do we make this new fluid sim when there is already existing solution? And the answer is that we have some specifics of wind that are not covered by the existing fluid sim solutions. And besides, why we didn't want to, for instance, take Fluid Ninja and extend it is that we wanted to keep our solution optimizable, in the sense that we can do all code optimizations, such as moving it to async compute eventually. When we have multiple sources, we want to be able to do culling on CPU and GPU and things like that. So for that reason, we wanted to have our own approach and to also involve modifying the core of the Unreal Engine. So for the fluid simulation refresher, I will not retell you all the theory from ground up, because first, that would take another lecture to do that. Second, I'm not the best person to do that. And third, there are great sources. Particularly, I want to refer you to Robert Britson book on fluid simulation for computer graphics. And recently, there was an EDX course. So particularly, take the first one. The following one are a little bit more specific to engineering. So here I want to give some sort of some things that I stumbled upon myself, and I think that could be helpful for somebody new coming to the field of fluid sim. So first of all, first thing that you want to realize, there is a huge gap basically between the theory of fluid simulation and the real time, or actually any simulation, because on one hand you have Navier-Stokes equation, and all theory you can find in the university program tell you how to solve it in very specific cases. But then when you want to solve it numerically, because there is no known analytical solution, if you know one, go to Clay University, claim $1 million. For us regular people on Earth, we need to do all this different weird stuff like McCormick advection, Helmholtz decomposition, which are completely unobvious from just looking at the equation, and Poisson pressure method. So you need to get ready to prepare yourself for this big gap between theory and practice. And second, I wanted to look smart, so I put this equation here. But the other reason is that I wanted to talk how to understand it, because basically, there are quite a few things that were not very obvious for me. So first of all, first step in understanding a Navier-Stokes equation is understanding it's not a Navier-Stokes equation, because essentially most of the time there is this term and this is a viscosity term. And if you take the GPU GEMS solver or any other solver used for real-time applications, nobody sane would try to really implement this in real time in an honest way. For dishonest, I refer you to my presentation on Tomb Raider. But a point is, removing this term, it simplifies it, because you don't have a second order derivative anymore, and makes it an Euler equation. So let's talk about Euler equation. And the thing here is that I wanted to go around different the terms that are not that easy to understand. So this one is easy to understand. G is just your external force, in that case, gravitation, but really any force. This one is the negative of pressure gradient, so that means when the fluid normally goes from the high pressure to low pressure, hence the minus and hence the gradient. But the question is, where does this one come from? And this is actually a great, if you study fluid, this is a great moment. If you had in your university program this full derivative and never understood why is that and why do you need it, this is a great point, because fluid, really it feels like fluids were made for full derivatives and full derivatives were made for fluids, because basically this is essentially this is the right side equation of the full derivative equation, which is outlined here. So on the right side you have this derivative over t of the complex of the function that depends on two derivatives, and one of the derivatives, x of t, also in its turn depends on this derivative. But you can think of it actually, the way to think about this and the way how to not lose your sanity is think of it as the Lagrangian specification of fluid and Eulerian. So that sounds fancy, but in layman's terms, Lagrangian specification is when you think of a fluid as basically a collection of particles, and you trace a life of particle, and you're basically just taking some small material element and see how its velocity changes over time, since there is just du by dt. And Eulerian, basically there are fluid solvers, but I've never wrote them, that use like Lagrangian approach. It's like those smooth particle hydrodynamics and all those scary words. And then most of the time, if you just write if you just copy paste your solver from the Shader Toy, that would probably be Eulerian approach, which means that you're thinking of a fluid not like collection of particles, but just some field on the grid, and you're analyzing the properties, how properties are changing in the grid cell. And what it says here is that there are two sources from which like a property in the grid cell can change. So first, it's just changing over time. So if this partial derivative du over dt is 0, that means that the flow is stable and it doesn't change over time. But that doesn't mean that if you move along the grid itself, that it wouldn't change. So basically, like. If you look here, here is our particles velocity. So if our flow is completely stable, that doesn't mean if you throw a new particle that its velocity will stay the same. No, because you can have like a steady flow that is going around something. And that is what this term is standing for. And essentially this term, if you remember like the full derivative equation, this is basically this du over dx by dx over dt, but written in the vector form. So this is like the dot product with a neighbor operator, which is like the per coordinate differential operator, and multiplied by u. So this u is basically dx by dt by definition, because it's velocity, and this one is your du by dx. So basically the way, and this term is also, so this is basically due to fluid motion, and this is what is called advection. So whenever you're writing this as advection step, you're basically accounting for this part of the equation. So this is all I will tell you about the math today, so you can now relax and just watch movies. So about fluid sim itself, there are, if we want to use it to simulate wind, there are the following things that we need to keep in mind. So first of all, as with the previous approach, we do want to have like scrollable simulation, and we snap it to the world grid as everybody does in those cases. So the idea basically is that you want to simulate fluid in some limited space because you have limited resources, and then basically you move it with your camera because you are not that interested in something that is like far than certain distance. Then you inject, during the simulation, you need to figure out how to inject velocity. And in case of wind, there are two main sources. There is a global wind, and then there are local motors. And unlike the God of War approach, we need to inject global wind as well, because we want it also to take into account obstacles. Then the wind simulation, I wouldn't dwell on it too much, because basically I just used the regular solver at this point, so there are plenty of sources you can read about it. And then finally, after you did all like this simulation, you end up with a velocity field. and then you want to fetch and use your wind in different parts of your, basically in wherever you want, and those places are typically the vertex shader, pixel shader, or basically simulation shader for particles. And now let's talk about global wind. And because PowerPoint is weird, only one video always starts, so that's why I keep my mouse with me. Okay. So basically, that is the biggest takeaway and the biggest point, like in this whole presentation, and the biggest like incremental improvement over existing stuff. So what is the problem? The problem is that we cannot set it globally again because we want it to be blocked by obstacles, and we want, and basically like we want to inject it somewhere on the boundary, and then like propagate it with advection and with progressive like solving like this pressure iterative solver. So, but the question is, how do we inject it in the way that is consistent? And what I mean by consistent is that we want to that our simulation area is square. But if we inject something on the board, if our wind is blowing, let's say, from the x direction, okay, we just inject everything on the x-axis. But if it's blowing under 45 degrees, then we somehow need to do something different. And we try different stuff. So we tried, for instance, so just inject from the two nearest direction, but the problem with it is that it's not providing uniform results. So when you change the direction of the wind, it will have different velocity values. And also, like when you inject from something like a corner like that, you can have some weird interference in those areas. So the solution that I arrived at was that we actually can always inject from the, let's say, from the negative x or positive x or whatever from this boundary. But what we can do instead, we can just take the whole simulation area and rotate it. So basically, because we can do that because we actually, like for global wind, we only have one direction. If we have multiple wind, we just add them together, get a resultant vector, and call it a global wind. So the main implication is that now, whenever we fetch from this texture, we would need to when we need to translate from world coordinates to texture coordinates, besides of scale and scale bias, we would also need to rotate the coordinates. But this is basically just some multiply adds on top of it. And then the other thing, the other implication, which is shown here, is that just like when we move the camera and we need to adjust, the same way we when we sample from previous frame, we need to do the same like for this. In case of a rotation, so we need to rotate back by previous frame rotation. So here on the top, it's we are not doing it, and you can see the moment we rotate the wind, everything rotates, and it's kind of hectic. And at the bottom, we're doing that, and basically when you rotate the wind, you see this delay when the wind starts blowing from the next direction. Okay, so let's talk about the local wind motors. So we tried different types. So the directional ones are pretty simple. So they have this like radial fall off. They blow in one direction. Then the wake motor. So we tried the same motors as in the God of War. The wake motors is just like it's attached to an object, and you can create a wind from there. And then vortices didn't really work that well because basically it's like we're trying to hack the simulation and hard code in it. So they probably we need to find a way to do it like in a PBR way. And the omni motors, they are a bit problematic. but they do work because the main use case for them is explosion, so we don't care about stability this much. But they are unstable for the reason that when we do the fluid simulation, we assume the fluid incompressibility. And if you think about omni motors that are just pushing everywhere from the inside, it's really never will be. It will never be preserving preserving pressure, because you always would need to have more pressure inside than, and it will all be going outside. So now let's go to where we use it. So and why? So in Pixel Shader you can use it for scrolling texture coordinates. In Vertex Shader you can use it for vertex animations, such as like grass going back and forth, and in simulation you can drive the particle velocity from it. And some tips and tricks, basically. So a thing you need to be really get used to debugging fluid simulation, and it's always painful because, as you can see here, one little mistake in simulation and it just blows apart and you have no idea. So what you need to do, like what I found out, I would just like make some synthetic case that I can work out manually and just go step by step and verify that that shaders are doing all the same, or that I somewhere forgot like to just copy pasted code and forgot to put the right coordinates. So, and you need some visualization. So a good one would be to have all color coding for it, numerical, so you can check the actual value and the direction as shown like here. The other thing is you want to keep it as physically based as possible. So particularly keep the velocity in world units, because you don't want to use arbitrary multipliers. Why is that? Is because if you, for instance, fetch the velocity and then multiply by it and put it on particles, yes, they will move faster, but the shape of the movement and the character of the movement would be radically different. For instance, you won't see this like nice mushrooming if they move faster. And then you also need to be very careful in the advection step, because you really want not to go by random amount, but by actual velocity, and that will sell you a lot of nerve cells. You want then to test it for different frame rates and different cell sizes. Probably there will be some issues, I would say. If it's like within 5-10% for 2x change, probably it's okay. If it's changing like almost proportionally, probably you screwed up something. And the most important part is that you need to find an owner on the tech art side, which would take absolutely zero crap from you when you will be explaining to him that, oh, sorry, this is how the fluid sim work, I have no idea. That he will point you out that basically, no, this is an issue with your implementation, and you would be able to work out your fluid sim like to cover all corner cases. So this is very hard, but this is what helps a lot. For Unreal integration real fast, so the main loop of simulation is basically like we're adding edge step as a callback to render graph, and then we bind the view buffer to every pass, because we use the shared constants in there. In frame, we basically put it as late as possible because we cannot go very early, because we need the SDF to put after SDF generation, and we need to we can't be between the pre-pass and the main geometry pass. So we reuse basically the last frame simulation. For constants, we pass it through view buffer because it's accessible in global shaders, in materials, and in Niagara. For obstacle vehicles, we use SDF provided from Unreal. It's kind of free because we need SDF for lighting anyway. And then we use the inbuilt intrinsics to sample it. And unfortunately, it creates coupled with lighting, so we cannot have something in some obstacle, something in not present in lighting and blocking and fluid sim and vice versa, but we'll live with that. For persistent data that is kept between the frames, it's only for us a velocity texture, and we store it in the view state and do the Q texture extraction at the end of the simulation. And then the previous frame data, such as wind direction, which is used for this reverse rotation, we keep it. We found out that the best place for it is fscene, and you can do the copy from previous to next frame in the start frame. And then you can bind it to view uniform shader parameters. So for the motors, we implement them in Unreal as components, custom components. For convenience, we have a custom actor, and the parameters there are blueprintable, so any artist can basically just attach a motor anywhere they want and affect it. And then we, at the back end, in fscene, we store an array of weak pointers, and when we need to modify, we fire up an enqueue render command to do it safely between the threads. And then we iterate over this array in the fluid solver. And the other thing is we only tick the wake components, and only when they move to be for performance reasons. Here we introduce custom nodes for pixel and vertex shader that just outputs velocity and does the rotation inside. And the same for Niagara. We do a custom data interface that fetches wind velocity. One more step for Niagara. In a Niagara data interface camera, we need to expose the params from the view buffer that are used for it. So hopefully you can see it later in the slide, because I need to accelerate. So now the few use cases. So this one is for the explosion. So you can see Omnimotor works pretty well despite it being unstable. The next one here, you can see how we have here a low wall and there is no wind happening behind it. The next one is the pixel shader example. So you can see the sand flowing under the influence of local motors. This one is with a wake motor, so we just put a wake motor on the character, and you can see it how it affects fluid sim. Also, you can see some visualization with color. And this one is a use case on Niagara, so we just put a wind motor over here, and you can see how it starts affecting those smoke particles. For performance, basically it's still unoptimized solution and work in progress. We tested it on RTX 3060, which is roughly what you get in the current gen consoles. 128, 128, 30 by 32 grid, we get about 0.7 milliseconds. It's 20 pressure operations. We still have full floating points, and we do it on graphics pipe. So there is a lot of things ideas how to optimize it. Fetch, you just for fetch, it's probably negligible in real life scenario unless you're doing some test on. For the future work, we want to do the following. We want to figure out how to properly do vortices, because that would be really cool. We want the compressible flow for the case of explosions, etc. We are thinking about pre-baked simulation. For some cases where we want more precision, we consider temporal stabilization, because sometimes fluid sim is noisy. And then we want to move it to async compute for performance. I really want to thank all of the people who made this work and presentation possible, and the whole PCF for letting me talk here. If you have any questions, feel free to ask in the remaining 1 minute now. Catch me after the talk. I will still be around here, or just if you're too shy, send them over to email. And as usual, if you want to work on cool stuff like that in the Unreal Engine 5, we're still hiring. So thank you a lot for your attention.